Good afternoon, my name is Geoffrey Chancel from the University of Montpellier, and I am going to present our paper called A Better Practice for Body Biasing Injection. To begin this presentation, let me present you some context. As you may know, BBI is a fault injection technique like many others, such as electromagnetic fault injection or laser fault injection, just to name a few. However, even if more work has been done in the past few years, it is still a less known method and many of its effects on IC's behaviors are unknown. Therefore, in this context, this paper aims at introducing enhanced BBI platforms allowing for better reproducibility and efficiency. Both theoretical and practical examples are studied. Then, we are going to present a differential fault attack performed on a hardware AES coprocessor based on the single-bit fault model from Christophe Giraud presented in 2002. Eventually, we will introduce a fault model allowing to explain the origin of faults in logic gates subjected to BBI. Before going deeper into this presentation, let me present you shortly the experimental platform equipment. The voltage pulse generator is an AV-Tech model able to generate voltage pulses from 50 volts to 750 volts with both negative and positive polarities, with pulse width ranging from 6 to 20 nanoseconds. The BBI probes depicted in this picture here are custom made using 3D printed parts, an SMA connector, and a spring-loaded pin allowing to apply constant pressure on the IC backside. Eventually, the target is microcontroller, a 32-bit microcontroller from ST Microelectronics, specifically the STM32F439 model, which embeds a hardware AES coprocessor, which is interesting in a fault injection context. Let us now switch to the first section concerning the enhanced platform for BBI. On the left here is presented a simplified schematic of a typical BBI platform in the state-of-the-art. The annotated values come from our actual platform. It consists of a voltage generator, a transmission line, in that case a 50 ohm transmission line, a BBI probe, an IC, and a grounding installation. On the right are displayed the corresponding platform signals during a simulation. In blue is the ideal voltage pulse, in green the effectively applied voltage pulse on the backside of the IC, in orange the pulse seen at the output of the voltage generator, and in purple is represented the current of the integrated circuit ground pin during the injection. What is important to remark here is that there is obvious ringing in every signal, in addition to failure to comply with the voltage set point of the generator, which is of 140 volts here, and we observe a 180 volt signal. This behavior of ringing and set point not being respected is not desirable in fault injection context, as we need precise and sharp signals in order to control finely what we want to achieve in the IC. To that end, we propose two improvements to the state-of-the-art platform displayed in red in the left schematic here. The first one is quite elementary and consists in bypassing the platform ground with short wires, low impedance electric wires. It allows bypassing the high measured ground impedance of this platform, indeed 150 ohms between equipment. In addition to this, we propose to connect a 50 ohms load directly at the output of the voltage generator, thus providing an approximate impedance matching. While impedance matching is not a new thing to reduce ringing, it had never been studied before for BBI platform and the impact on BBI efficiency. Then, when observing the signals on right, we can observe that the voltage setpoint is a little bit closer to the required value, in addition to having a lot less ringing. Every signal has a lot less ringing, which is beneficial for precise and controlled impulses. Now that we have seen the theoretical improvement, let us analyze actual experimental results. As before, two scenarios are presented. On the top, the state-of-the-art scenario, and on the bottom, the enhanced platform. For each case, we are going to look at two signals: the voltage pulse observed at the generator output and the current measured at the IC ground pin on the right. In each scenario, the set point is a negative and 140 volts with 20 seconds pulse width. The first important thing to note here on the voltage waveform concerns the pulse width. Indeed, the pulse width is more than 3 times higher in the state-of-the-art scenario, as we can see here, while it is perfectly matched in the enhanced platform. In addition to this, as we predicted before, the voltage set point is closer to the requested value, with an undershoot going from 100% in the first case to only 30% in the second case. It is not perfect, but it is an important, significant improvement. Eventually, the ringing reduction is very noticeable, especially on the ground current waveforms on the right, where the disturbance duration is shorter, which is equal to the pulse width in that case, while the amount of energy stays roughly the same between both scenarios, the energy transferred into the IC, as we can see with the RMS current flowing through the IC ground pad. Following this very simple experiment, let us now look at more complex and more complete experiments. To verify the soundness of the enhancement we propose, we decided to perform in the first place what we call fault susceptibility analysis. These experiments, shown here on the top of the slide, consist of measuring the minimal current required to induce a fault at every location on the backside of an IC, in that case the STM32. This experiment allows spotting sensitive areas of the IC. At first sight, the most obvious difference between both scenarios is the drastic fault area reduction from the first to the second scenario. It might look like a downgrade from one platform to another, but it is not in fact. The ringing reduction easily explains the area reduction. Indeed, as we have seen before, the disturbances flowing through the IC is shorter and more precise with the enhanced platform. Thus, it reduces the area that the BBI is targeting and thus blocks further location to fault at a specific location from the BBI probe, of course. In order to analyze deeper the platform, we decided to perform a differential fault attack, as I have seen before. More specifically, we chose the bit fault attack proposed by Christophe Giraud in 2002. However, because this attack requires very specific fault types, in that case single bit and monobit or multi-bit faults, instead of measuring the minimal required current, we did similar experiment as before, but instead we analyzed the fault type at each location just around the AES coprocessor, not on the entire IC. This is the two mapping here that I am presenting. In that case, there are 7 fault types, ranging from correct behavior, which is in blue in that case, monobit faults in yellow and cyan, which are useful for the attack in that case, multi-bit faults in magenta and orange, which are completely unusable for this specific attack, and more extreme behaviors such as recoverable crash in gray and unrecoverable crash, alias timeout, in black. The experimental conditions in each case were set such as to minimize microcontroller crashes as much as possible, and of course to maximize reversible faulty behavior. The main noticeable difference between both cases is the amount of microcontroller crashes on the left. Indeed, most locations exhibit a crash, which is not desirable, of course, as we cannot use any data because most of the time the microcontroller does not return any useful value in that case. On the right, however, we observed no crash at all, and it was done with much less effort to find the perfect experimental parameters. Indeed, we observed 5 useful locations where monobits were observed in that specific case. So let's see now the practical attack results. Sweeping the 5 found locations previously allowed us, with only 3 of them, to recover 14 bytes of the last round key, aka the secret key in that case, because we are using an AES 128 bits. However, despite all our efforts, it was impossible to recover the last 2 bytes, indeed the number 2 and 5, more specifically, thanks to this fault attack in any of the 5 locations. Nevertheless, with 16 bits left to find, it's only 2 to the power of 16 combination in the worst case scenario in a brute force attack, considering that our platform computer can perform 180,000 encryption per second. It would take less than a second to find the remaining bytes. Now that we have seen the improvement in practice, it is important to elaborate a fault model in order to be able to understand the mechanism behind fault creation during body biasing injection. To begin with, let us take a look at the elementary electrical models on the left, put in parallel with a silicon side view of a logic inverter on the right. In that case, we will focus on triple well ICs exclusively for simplicity. We already introduced these models in past papers, but I am going to describe them shortly for clarity. A standard cell segment on the left represents the average electrical behavior of a portion of an IC in this model. It does not represent the function of the IC at all. In addition to this, each model can be duplicated as much as needed to compose an entire IC, which can then be simulated. The models are composed of 6 main regions. The first region, numbered 1, is simply the silicon substrate, simply composed of electrical resistances. The second region represents the substrate junction with the N-well, located here in the right schematic. The third region is the junction between the N-well and the P-well, which is deep inside the N-well, with, as before, an access resistance from the substrate to the top of the IC, a diode and a capacitance representing the junction. The region 4P and 4N are the average N side and P side of the logic gates transistors. The region 5 and 5' are the power delivery networks, and eventually the region 6 is the decoupling existing between both power delivery networks. With that in mind, we simulated then a 270 by 330 micrometers IC with a thickness of 100 micrometers, which represents 2,376 standard cell segments interconnected together. As before, we will be comparing the state-of-the-art platform with the enhanced platform. In this slide are presented the signals extracted from the previous simulations of the entire IC for each platform. The first 3 signals are circuit-wide, while the other 7 are local signal extracted from the standard cell located just directly under the BBI probe. From up to bottom and left to right, the signals are, in order of appearance, the generator voltage pulse in green in that case, the current delivered by the generator, the current measured at the IC ground pin in purple, the local GND voltage, the local VDD voltage in the standard cell, the current going from the substrate to the top of the standard cell flowing through the epitaxy level being the last level at the top of the substrate before the transistors and everything. Then we have the differential supply voltage, the epitaxy voltage, and the voltage at the junction between the P-well N-well and the N-well substrate here. What we can say here in the first place is that the approximate impedance matching on the right, in addition to the ground bypass, helps a lot the generator to produce clean and sharp disturbances inside the IC. It can be seen in every waveform. Every single waveform is cleaner with less ringing, with values closer to the required one. However, because the models we used previously for our simulation do not represent any functional behavior of any IC of any kind, we decided to fully appreciate the benefits of the disturbances improvements that we observed in the enhanced platform. We decided to extract the signals from this simulation and to inject them in real, actual, functional logic gates, in that case CMOS inverters. More specifically, two inverters, one with a normally high output and another one with a normally low output. Here are the simulation results of such simulations. As before, we compare the state-of-the-art platform on the left and the enhanced platform on the right, and the colors correspond to the signals depicted on the left schematic of the inverters. We show here 7 signals: the voltage pulse in orange, the differential power supply in black, the total current going in and out of the normally high inverter in that case in green, the current flowing through the inverter capacitive load in magenta here, and of course the logic gate output in cyan, the normally high inverter, and in blue the normally low inverter. The first significant thing to notice here is that the current going out of the load escapes through the transistor power supply. In the normally low inverter, the charges exit through GND and the P-well, and in the normally high inverter, the charges escape through VDD and VN-well. In addition to this, the normally high inverter in that case is pulled low for 20 nanoseconds, a bit more than 20 even, exactly 22 nanoseconds. While on the left side, on the state-of-the-art platform, it's pulled low for only 8.5 nanoseconds, while the pulse width of the generator in that case is of 20 nanoseconds. Therefore, in the second scenario, the amount of time the inverter is pulled low is almost equal to the pulse width, which is a desirable behavior in order to precisely control how much time an attacker wants to disturb an IC. Then, concerning the normally low inverter in the state-of-the-art scenario, it is pulled high on the second edge of the pulse, while on the enhanced platform, its value is pulled low and then returns to 0, which does not change the logic value of the inverter. Therefore, what we can see here and conclude is that the enhancement we propose allows to fine-tune the disturbances, characteristics, duration, voltage, and everything, while on the state-of-the-art platform, the disturbances are subject to ringing, and then, depending on the platform characteristics, like the length of the transmission line or the impedance of the IC at a specific location, all of these parameters are going to disturb and avoid any precise control of every disturbance inside the IC. To conclude, the enhanced BBI platform we proposed simply consists in approximately matching the voltage pulse generator impedance, which is not expensive and easy to set up on existing platform, in addition to bypassing an imperfect grounding platform grounding. It allows having a better control over the various platform parameters, such as the voltage side point, which is important, the pulse width, which determines how much time the attacker disturbs an IC, in addition to bringing better repeatability over various platforms thanks to the reduction of ringing. Then we managed to conduct a differential single-bit fault attack, which was impossible despite every effort with the state-of-the-art platform. Eventually, we also brought an additional step to the previous simulation flow, allowing to simulate the behavior of isolated logic gates and their BBI in addition to electrical, not functional model. Thank you very much for your attention, and then I will be pleased to answer any of your questions.